Okay. All right, so like I said, in order for us to understand waveforms or radiation, we need to understand the nature of a wave, basically. Okay, what am I doing here? Let me go back. Got it. Share my screen. Okay, so if you imagine, and I'm quite sure you guys probably did this as kids, let's say you have a rope and the rope is attached to a fixed object like a wall, and you hold the other end of the rope and you do this up and down motion, right? Then we all know what's happening after that. There'll be a waveform that's generated by the rope, right? And it will look something, and please, I'm quite sure you guys already know that I'm not blessed with artistic skills, so please forgive the rough looking appearance of what I'm about to draw, but let's say the result is what we have here, right? So that's the waveform, right? And there are several characteristics of the wave that you need to know in order for us to examine radiation. The first of which is the distance between two successive equivalent points on a wave. Now you can choose those points to be like, for example, the apex or the maximum point of the wave here. That distance, we call that the wavelength. And we traditionally use the Greek letter lambda to represent that, right? So lambda is equal to the wavelength. And the wavelength can be expressed in pretty much any unit of length, right? Could be meters, centimeters, etc. Right? So that's one characteristic which you need to be aware of. Another one you need to be aware of is what is called the frequency. Now, the frequency is represented by the Greek letter nu. And the frequency, I'm just going to write down the definition here, is equal to the number of wave cycles that passes a particular point per unit time. And invariably, the unit of time would be seconds. I've never seen the unit of time in this particular context expressed in no other units. All right. Now, as a result of that, the actual units of frequency, will be expressed as seconds to the -1. Because remember, it's a number of wave cycles per second, right? So that's why it's seconds to the -1. And there's a special name given to this unit. It's called the Hertz unit. And the symbol for Hertz is Hz, right? So seconds to the -1 is the same thing as the Hertz unit, all right? So those are a couple of things that you need to be aware of when it comes to waveforms. Another thing you need to know about the waveform, another characteristic, where am I going to squeeze that? Let me see if I can scroll down here. Oh no, I guess. Okay, I'm going to do this up top here. Is the speed of the wave, represented by V. V for velocity or speed, right? And that is equal to the wavelength times the frequency of the wave, all right? Now, the units of velocity is dependent on whatever unit you have for both wavelength and frequency. Typically, in this equation here, the wavelength unit would be in meters, and the frequency would be in seconds to the -1, which is the same thing as hertz, which means that the velocity of the wave would be expressed in units of ms to the -1, which is the same thing as meters per second, all right? So that's a relationship between the velocity, the wavelength, and the frequency, and this is true for any waveform, all right? Now, specifically as it relates to electromagnetic radiation, and there are various forms of electromagnetic radiation. And I'm just going to show you what we call the spectrum, right? It turns out that the speed of the wave is equal to a constant, which is traditionally and conventionally expressed as c. And that is equal to a constant value, which is 3.00 times 10 to the 8 meters per second. All right? So that's the speed of all forms of electromagnetic radiation, without exception. All right? So basically, when it comes to electromagnetic radiation, C would be equal to lambda times nu, right? And because C is always one value, that means that there's an inverse relationship between the wavelength and frequency, right? In other words, if the wavelength is large, the frequency will be small, and vice versa, right? Because when they multiply, it's equal to one constant value, all right? Now, with that said, let me, oh, do I have it here? No, I don't have it here. Shucks, I should have brought my thumb drive. Okay, let me, I have to get into another course here to show you this particular spectrum, the diagram which shows you the spectrum, all the forms of radiation. So this is my introductory chemistry class. And let me go to the lecture notes for that class. And let me go to here. I think it's located. Okay, this thing is taking its time. Okay, scroll down. Okay, so this here is what is called the electromagnetic spectrum. It's basically a list, a chart, which gives you all forms of electromagnetic radiation. And in this case, they have them from the lowest wavelength to the highest wavelength, left to right, right? So basically, these are different forms of radiation. And if I were to start from this end, the lowest end in terms of wavelength, we have gamma rays first, all right? And then we have X-rays, all right? And these are the values here of this scale right here, 10 to the minus 12 meters, 10 to the minus 10. And then you have ultraviolet radiation. And then you have a narrow band here, which is called the visible part of the spectrum. That's basically the different colors of light that our eyes can detect, all right? So it starts off here. In fact, there's a what do you call it now? An abbreviation or a mnemonic you can use to remember the order. I remember the order in the opposite direction. Red, orange, yellow, green, blue, indigo, violet, right? So this order here, going in this direction, is in this direction right here, all right? So that's a visible part of the spectrum. As you can see, it's a narrow range within the wider electromagnetic spectrum because our eyes cannot detect gamma rays, X-rays. We have to use instruments in order to detect those forms of radiation. And I remember reading somewhere, don't know how true that is, that only the women or the female of the human species can tell the difference between indigo and violet. I don't know how true that is. It's probably true because I can't tell the difference between those two. All right. And then after that, you have infrared and then microwave. And then the higher wavelength radiation would be the radio waves, which include TV and so on. All right. CB radios, whatever. All right. So that's basically the electromagnetic spectrum. And as I said before, write this down here, that C is equal to lambda times nu, which is equal to, as I said before, 3.00 times 10 to the 8 meters per second, all right? So what that means, therefore, is that as the wavelength increases this way, so let me put an arrow here, this is increasing wavelength, then the frequency increases in the opposite direction, increasing frequency, all right? So that's basically the relationship between wavelength and frequency, all right? And we'll probably get in, well, at this level, we won't get into it in any great detail, but there's actually a relationship between the wavelength or the radiation and the atomic structure of atoms, which we'll get into, may or may not get into in any great detail. Okay, so for now, what I want you to do is do these questions. Now, I'm not sure if we'll be able to complete all of this handout today, but we can at least get a start to it. So basically, the questions in this handout is utilizing that equation that I mentioned, the relationship between frequency, speed of light, and wavelength. All right, and basically, well, let me get you started on the first question. Let me get out of this here and go back to my writing tablet. And let me clear this here. Okay, so the first question says that what is the frequency in hertz of blue light having a wavelength of 425 nanometers, right? So remember we said that C is equal to lambda times nu, right? What the question is asking for is nu. So by rearrangement of the first equation, you're going to end up with C divided by lambda, right? Now C is always going to be equal to 3.00 times 10 to the 8 meters per second divided by the wavelength. Now what's a wavelength? The wavelength is 425 nanometers, right? What we have to do is convert that into meters, all right? Now there's a table that I provided for you, which helps you. You don't need to memorize the relationship, so that's why I provide a table. Let me see if I can find it. Let me go back to this course. So files, and then tables, and then, let me see here. Tables chemistry, download. This. Okay, so this table here, let me turn it around right side up. Okay, so there are two pages. You have this page and then you have this page right here, right? This table here, I don't know if you guys are familiar with the metric system, right? The metric system is basically the system of measurement, which is more convenient and more versatile compared to the, what do you call it now, the older system, non-metric system, let's call it that. And the reason why it's very convenient and versatile is because basically the difference between larger and smaller values is by a factor of 10. So for example, if you see, like for example, here you see the list, deci literally means 10 to the minus 1 or 0.1 of whatever the unit is. Centi means 0.01 or 10 to the minus 2. So for example, I can say that, let me do this here. So for example, based on this centi prefix, which means 10 to the minus 2 or 0.01, I can say that 1 centimeter is equal to 0.01 meters, all right? Because the centi prefix here means 0.01, all right? So that's basically how we use a metric system to convert from larger units to smaller units and vice versa. So you'll notice in the question, for question number 1, they gave you that the wavelength is in nanometers. So nano is the same thing as all this here, or more conveniently, 10 to the minus 9. So therefore, we know that 1 nanometer is equal to 10 to the minus 9 meters, because the nano prefix is the same thing as 10 to the minus 9. All right? Now, the reason why I mentioned that, let me get out of this here. Let me go back to this here. Oh, you know what? I guess I need to erase. I need to clear this. Okay. So the reason I mentioned that is because the nanometer unit here cannot directly cancel out the meter unit, right? So we have to convert that nanometer unit into meter unit. And we know that 1 nanometer is equal to 10 to the minus 9 meters. So this is how we have to set it up, right? This nanometer unit will cancel out with this. And therefore, all we have to do is the rest of the number crunching. And we get the answer. So let me do that right now. 3 times 10 to the 8 divided by 425 times 10 to the minus 9. And according to my calculations, this works out to be equal to 7.05 times 10 to the 14, I'm sorry. Right? Because this nanometer unit will cancel out with this, and this meter unit will cancel out with this. So you'll be left with S to the minus 1 or hertz as your final units. And this would be the answer. All right. And that's basically pretty much how question number 1 is done. So a couple of things I want to point out here. So what you'll find in each of these questions in part A, so we'll be focusing on part A for now. Basically, you have to ensure that the units are such that they're compatible, right? If, for example, you have a nanometer unit expressed for the wavelength, you have to convert it to meters because the units for the speed of radiation, C, is in meters per second, all right? As far as hertz is concerned, you don't need to convert because, again, meters per second is, well, for hertz, the units will be seconds to the minus 1, so that's compatible. But what you'll find in a couple of these problems is that you have to convert the units in some cases from some unit of length, like nanometers or centimeters, to meters, all right? And then you do the rearrangement of the equation and solve for whatever the question is asking for. All right, any questions about this particular solution for number 1? Any questions? Oh, I just put the numbers in the calculator. Right, so like what I did was I put, let me just say something. I don't know if I mentioned this to you guys. When it comes to your scientific calculator, you have to be very careful how you use it in order to express numbers like this in scientific notation. So it depends literally on the brand of calculator that you use. Like this calculator is a cheap Casio calculator. If I were to enter 3.00 times 10 to the 8 in this calculator, I would have to press 3, and then there's a button here which says EXP, which stands for exponent, and then I would put 8. And then on my calculator display, this is what it literally looks like. 3, and then you have 0.8 here, right? That's what it looks like on my calculator. That, according to the calculator, is the same thing as 3 times 10 to the 8, all right? So it all depends on, and that's, you know, that's my calculator. So yeah, you guys have to be careful about, you know, how your calculator deals with expressing numbers in this way, all right? But that's all I did. I just put the numbers in, and that's, you know, the result I get when I hit the equal sign. Okay, any other questions? Any other questions? Any other questions? All right, so let's see if we can do, let me clear this here. Let me get out of this here. Let me do, okay, so the next question says, a certain substance strongly absorbs infrared light having a wavelength of 6.50 liters. So in this case, I mean meters, I'm sorry. So lambda in this case is equal to 6.50 meters. And the question is asking for the frequency, right? So again, the equation we're going to use is C is equal to lambda. Okay, where's the eraser? Okay, so hold on, let me get back to my okay, so remember now C is equal to lambda times nu, right? So in this case, the question is asking for nu. So rearranging this equation, you're going to end up with nu is equal to C divided by lambda. And as we said before, C is always going to be 3.00 times 10 to the 8 meters per second. And the wavelength is 6.50 meters. Now, in this case, we didn't need to convert the unit of length to meters because it's already meters, right? So all we have to do now is plug the numbers into our calculators. So 3 times 10 to the 8 divided by 6.5, whoops, 6.5. And according to my calculation, this works out to be equal to, now in this case, it's more convenient to express this in scientific notation. So according to my calculation, this is 4.62 times 10 to the 7. And the units here would be seconds to the -1 again, because this unit will cancel out with that unit. And that would be the answer. All right. Any questions about that one? Any questions? Okay, let's look at number 3. Now, let's see if you can do 3 without my help. It says, it talks about ozone, and it says that the UV light having a wavelength of 295. Let me write this down. In fact, let me just get rid of all this here. Okay, so the wavelength in this case is equal to 295 nanometers. And the frequency is what the question is asking for. So how would you solve this problem based on what we have done so far? And let me remind you that C is equal to lambda times nu. That's the equation that we're using. Okay.
C over, C over lambda.
Okay, so nu, whoops, is equal to C over lambda, right? And then what?
3.0.
3.00 times 10 to the 8 meters per second, divided by the wavelength, which is, okay, exactly, 295 nanometers. So if you remember what we did, what would be within the parentheses, what would be up top here and at the bottom here? If you look at the first example we did.
10 to the -9.
Okay, so 10 to the -9 would go up top here, meters, and down here.
That's 1 nanometer. Right?
Exactly. And that's it. Let's see what that gives. 3 times 10 to the 8 divided by 295 times 10 to the -9. And according to my calculation, this works out to be equal to 1.02 times 10 to the 15. And again, the units would be S to the -1. Okay, so I'm going to leave you now to try the rest. If you have any questions, of course, feel free to ask. Finished? Okay, what don't you get?
The scientific. But like also taking.
Which question? 4, okay. All right, so in the case of 4, let me
Yeah, everything. One.
let me share my screen. Let me okay, so for number 4, it says what's the frequency? So the equation you're going to use is nu is equal to C over the wavelength, right? And C is equal to 3.00 times 10 to the 8 meters per second divided by the wavelength. Now, the wavelength in this case is given in centimeters, right? And if you go to the same table I showed you, you'd see that centi is the same thing as 0.1, right? So 1 centimeter is equal to 0, no, wait a minute. I'm sorry, it should be 0.01, right? So centi would be 0.01 meters, all right? So basically, you're going to put 1 centimeter down here because you want the centimeter units to cancel out. And you're going to put 0.01 meter above. And therefore, when you, again, it depends on the calculator. What kind of calculator do you have? Oh, you have a phone. I don't know if your phone, oh. Well, that means that in the case of 3, on your phone, you'd have to write 3 followed by 8 zeros. You see what I'm saying?
What I've been doing is I've been trying to just get everything set up and then I'm like, calculating this at home too, and I'll just solve it when I
Right.
get home.
So 3, if you're going to use your phone, is 3 followed by 8 zeros. But on my calculator, I'll do 3 times 10 to the 8 divided by 3.19. 1. So according to my calculator, I got 9.40 times 10 to the 9. And the answer, the units would be seconds to the -1. And that's it. Okay, listen up. So, you can finish up on, this entire assignment because I've posted the videos for section, for part B that deals with, electron configurations. So you can watch those videos and, if you have any questions, feel free to contact me, via, Skype or in person. And also, I'm going to post some more videos for some other topics in chapter 3. So make sure you watch those videos as well in preparation for next class. All right. So I know I'm keeping you busy with that, plus your preparation for the test, all that good stuff, but at least it will keep you out of trouble. So
Are you gonna send it out this weekend, just when you can actually sign up for the test? That looked again right before class started, it still just says general.
oh, okay. Yeah, I'll do that. Yeah, I'll do that. As soon as I call over there, I let them find out what's going on, and then hopefully I would expect they'll be able to make the appropriate changes. And then I'll make an announcement. Yes, ma'am. Okay.
You have a good one, we'll see you next week.
Yes, sir.